share the screen. All right, so we are now sharing, okay? We've started. So let's go over here. Here we are. Yeah, so today I have on the agenda, as I said, we're going to do some of the presentations of the GPT that you guys are fine-tuning with reinforcement learning through human feedbacks. So that's towards the end. Otherwise, the lecture is going to continue where we left off last week. If you remember, we're talking about reinforcement learning as a third stage or a third phase of training. We have pre-training, fine-tuning, right? And those are basically supervised, essentially, or semi-supervised. And then we have a third phase, which is reinforcement learning, in particular, reinforcement learning through human feedbacks. So we've started with a baby RLHF with PPO, okay, and I'll come back to that code. We finished it, but I want to go back to it. We'll do that next week. Today, we're going to dive into a little bit more of the theory, the math, the loss function of RLHF PPO. Okay, just dive deeper. I have a few, I prepared some material for that. And then, of course, it kind of in parallel, if you remember, I said reinforcement learning has like two big families, policy-based, like PPO, and then Q learning, right? So these two families. So I've given you the example of PPO, but I've also started talking about Q learning, right? So I gave you the basic example of Q learning with a table last week, and we had a whole environment there that we can play in, right? So I'm going to continue that discussion today, but we're going to replace the table with a neural network, right? So we're going to talk about a neural net, so it brings in more, but so we're going to do that example. So, yeah, so those are the things, but really I'm kind of finishing from large language models as we are going to move to another area. But what's interesting about this is the techniques that we're using in large language models, right? Like pre-training, fine-tuning, reinforcement learning, even through human feedbacks, can go along with us on this trip, right? So we can use it for when we're training models for images like ResNets, and we can also use it for time series. So the class, I've divided it into like 3 mediums, language models. That's the first one. The second one is going to be time series. That's what we're going to move into. And then finally images like ResNets and generative type of things where we can fine-tune ourselves to be a cowboy, a cowgirl astronaut, something like that. All right, so, but as I said, we carry along the methods. So RLHF with PPO, we can carry along for a time series, GPT, for instance, something like that. All right, so yeah, so let's take a look then briefly. Let's go back here to the table of contents. And let's actually look at the syllabus. I just want to go over the description of the syllabus a little bit. So, we cover the theory and technologies related to deep learning. In particular, the course focuses on following topics: neural networks and hidden layers. So, any neural network, deep neural network. Issues with designing deep neural networks. So that's, what we're doing with pre-training, fine-tuning, RLHF. So all that we're covering as far as the methods, convolutional neural networks, and anything related to images, right? So I will, towards the end, hopefully, get to stable diffusion. The next big one is this one, of course, recurrent neural networks, right? So that's what we're going to cover, hopefully, on Wednesday next week. All right, so be ready for that. So obviously, we could use now recurrent neural networks were used before transformers in language, but they weren't very effective, right? So they have essentially been totally replaced in language tasks, right? So RNNs were the big thing back in 2016, right? But 2017, we got the transformers paper that changed everything, right? Because these don't scale very well. I mean, they've made improvements now where, of course, they have attention and all kinds of things like that. but still transformers are way better for language. However, RNNs can still be used for other tasks. And one task where it's commonly used is time series data. Do you guys see that? And so that's where, because time series data, if you go to conferences and things like that where you have specialists in time series, they're still using classical methods. They're still using your famous ARIMA and moving averages. And I'm not saying any of that is bad. They're very effective. They use them in the stock market, all that stuff. But the neural network or deep learning algorithm that would tie to that would be RNNs. Okay, so I will do an example next week actually with images to kind of introduce images also into that realm. And from there, we're going to do apply it to time series. Does that make sense? So that will be the next algorithm that we will implement in PyTorch, and there's going to be a focus on that time series for a few weeks, including extending. Okay, so I'll try to make the connection of, okay, we did time series with RNNs, but so let's think about this, right? So for language, they were using RNNs, and then they shifted towards transformers, correct? GPTs. So if we can use RNNs in time series, could we make the shift to GPTs? Do you see what I'm talking about? Because they are sequential. So we're going to explore that, okay? And that might be actually one of the assignments I give you, okay? So it might be to train a time series GPT, okay? And hopefully it's the same as 520, the same language model, but just adapted to the problem of time series. So we'll talk about that then. And what's interesting is, as I was saying, not only can we pre-train that time series GPT, fine-tune it, but we could also do reinforcement learning through human feedbacks, right? Because in a time series, for instance, what are we predicting? We're predicting, let's say the price of the stock market, or gold, let's say, right, for the next week. Gold, the price of it, right? So it's fluctuating. So how could we use it in the context of reinforcement learning through human feedbacks? Well, we have a model, and it builds two predictions for next week. So we have one graph that goes like that, and another one that goes like that, right? And we have maybe the real one. So now a user, a human, can come in and say, I don't know how to produce those things, but I can tell you which one I like. I like this one. Do you see that? You see that how now then that can become reinforcement learning through human feedback. And then we use the exact same mechanism. So that's what I want to stress, is that these techniques can be used for anything, really, stable diffusion, whatever it is, because it's all neural networks that backpropagate the weight. So essentially the techniques are kind of like a parallel of the algorithms for the specific mediums, like text, images, and so on. Okay? So that's kind of on the agenda. So next week we start with recurrent neural networks. And we'll spend a few weeks on time series generated things, but still touching on issues with designing deep neural networks, like the techniques and so on. Then once we move into images, of course, we'll pick up where we left off in 520 on GANs. I think I only did it very briefly there, and here you'll have like a homework assignment on GANs, and then stable diffusion, which are essentially generative image generators, right? So, yeah. Word embeddings we've covered, and then, special topics and things like that. Okay, so this is where we're going. Okay, so I just wanted to, I've definitely prepared this lecture for next week, and it'll be with MNIST, essentially, for the recurrent neural network. Okay, so any questions so far? No? Okay, great. So now that that's covered, let's go into the topics for today. So, I wanted to stress that so that you knew that all this reinforcement learning does continue, and as we move forward. All right, so today I want to talk about two things, which are, we're going to go back to Q-learning, but a deep neural network. And then, as time permits, I think, here, right? PPO, yeah. Right, and here we're going to continue where we were last week, we went over the baby RLHF PPO. We went over the code. I'm still working on improving this code a little bit, but we're going to discuss a little bit more today of the, where is it? Of the equation. So PPO, RLHF, more full mathematical objective, and some of the deep insights. If you remember, this is the equation, correct? You guys remember, this is the equation. So can you guys tell me what these terms mean? So this is the loss, right? What was this one? The what? No, that's not the reward. See, this is a common confusion, right? In, what is it?
Is that like a gain?
It's the ratio, remember?
Yeah.
That's that ratio that we were talking about, and it can confuse you as you look at it in the paper. Remember, it's that we did the log probs thing? Yeah. Now, what is the A then? This is how it is in the paper. What's the A? Which is in terms of the reward. That's the key thing that you have, if it confuses you what the advantage is, some strange thing, perhaps, but just say it is in terms of the reward. So it is a reward of some form, but modified. Do you guys see that? And then this is just a parameter like, a weight, a cost. This is the KL divergence, which is the difference between the probabilities of the policy new and the policy original, which is different from policy new and policy old, which we had talked about last week. Do you guys remember? All right, so we'll talk about these two things. So let's start here, okay, just to kind of continue this, and then the Q learning with a neural network will actually go into the code. But today I just, we spent a lot of time in code last week, so today I want to kind of like bring everything together, okay, and the math formality. All right, so let's take a look actually at the paper. All right, so I'm sure you guys have read this paper many times already, right? It is a very important paper. Definitely take a look at it. I think it's one of the more fundamental papers for this type of thing of like designing these models. So it was the Siegler 2020 paper, if you remember. All right, and this is where they use fine-tuning language models from human preferences, right? And like I said, what's nice about this is the whole premise when you don't know how to train a robot to dance salsa, right? Or you don't know what is a good question and answer. Or you don't know what's a good prediction of gold, of the price of gold for the next month. Do you know what I mean? How do you figure that out? How do you write that equation? Well, maybe you can't, but you can look at two and say which one is better. And actually, that may be something you can automate, as we will see later on. So that can be applied to lots of things as the underlying. So, read through the paper, of course, but we'll start just essentially here. So this talks about probability distributions of sequences and things like that. So this might be confusing sometimes where we think there's a table and we think that transformers or GPTs have a table of probabilities. There is no such thing. You can't just like go in and what's the probability of this, like we did with the embeddings of the autoencoder. Instead, we have to run things through the GPT to get probabilities, right? Because it's the example of bank of the river versus bank, the financial institution. If we wanted, let's say, an embedding of probabilities of the word bank, right, we have to give it actually the whole sentence so that it produces that for bank. It's going to produce one embedding for bank of the river with the sandy thing, right, versus the bank, the financial institution where you keep your money. Do you guys see that? So you have to run things through the GPT instead of just extracting it somehow. Does that make sense? That's the first key thing. All right. Then the second thing, this talks about a lot of things, but here is essentially our equation, right? This is our loss. This is in RLHF, this is the thing that we're trying to optimize. Okay, so this, essentially is the function, and this is but this is going to be in terms of the ratio and the reward, right? So that's the key aspect. So it's, it just breaks it out into parts here, and then there's the clipping effect, and I'm looking for that. Yeah, so this is the clipping, kind of that same idea. Okay, so let's look now at we kind of start with this idea here. All right, so let's go to the notes. So I have this kind of more broken out into these things. Okay, so the core PPO RLHF mathematical objective. So this is the simplified policy optimization objective used in RLHF. So we have this probability ratio, right? And this is in terms of that clipping, right, that we were discussing, and we'll come back to. There is multiplied times an A, which is called the advantage. But like I said, if it's confused, notice there's no reward mentioned here anywhere, right? So that advantage is in fact in terms of the reward, okay? And then we have the KL weight, which is just to indicate how important. This is actually important. This essentially is, if you make this too low, then the model changes a lot. If you make it too big, then it changes very little. Do you see that? So it's a very important control. And KL divergence, KL is the divergence from the base model, so that the model doesn't change that much as, it's like it starts chasing the reward and it can become completely different, okay? So one way of thinking about this is that there's only one thing that's being optimized and there's two controls. Do you see that? So what is the thing that's being optimized? The advantage, which is the reward, okay? And the controls are what? This one, the ratio. This ratio with the clipping controls it. And also the KL divergence controls it. Do you see that? So they're more breaks than anything else. And the thing that you're changing is the reward itself, or trying to optimize, okay? So just like in Q-learning with the Bellman equation, we were trying to get those rewards also, right? And so that was the idea, and our goal is to get more rewards, essentially. That's how we measure performance. Got it? Does this make sense? Okay, so, and the reward comes, for instance, in our example, from a bird, right? So we look at, or humans can also provide the feedback. So remember that we've already discussed that in actuality, we do the difference of logs, right? But just to keep it more in the context, of an intuitive context, I'm going to use the ratio here, okay? But just we formally express it as a log. So the true ratio form, so this directly measures how much the model increased or decreased the probability of choosing a token, or a whole construct like a sentence or a phrase, okay? So essentially, and I have an example for this, so we'll discuss this in a second. But it's a ratio of, here's the GPT, text goes in, text goes out, right? So you're going to imagine you have the old and the new, the same text, and it goes in to both. And then you get outputs, correct? But those outputs, before you got them, they were what? Logits, and those distributions of the probabilities. Do you see that? So that's one way of, so essentially we don't need the actual output text, we need the phase before, which is the probabilities essentially. The log, if it's a softmax of logits, it's like a probability. Do you guys see that? But exactly, let's think about that, how that would work a little bit in a second. But remember, the little pi, that just means the GPT itself, also formally called the policy, okay? It's the model. Remember, it's not the original model when we started, right? It's the model every iteration, right? So every iteration, And that's, like in my code, I had old and new. Really, it should have been more like the Q-learning code, right, where we just had it once and we're kind of saving the old. Do you see that? So every iteration, how much did we change? Because it's a control, and it's actually, you can think of as you're essentially controlling how much you're changing. Do you see that? That's essentially the idea. Don't get too far away from the original, and also, that's like a global break. I couldn't think of an analogy, but there's like a global break, and then there's like a more fine-grained tiny break as well. And this is more of a tiny break if we think about it that way because of that clipping effect, right? So don't let the probabilities change that much. We've already discussed this part, so I'll just skip that, right? That's just the ratio, because of logs, becomes a difference, okay? So PPO uses the log probabilities to maintain numerical stability, make it more easy to compute. So, as I said, the ratio is a control, so the ratio is not the optimization target. What's the optimization target? Should be the reward, right? Or this advantage, which is some kind of a reward modified. And we will look at that. And it's essentially, I can also mention that already. So I could get a reward, it's like a 5, right? Okay, and that might be a really big change because it's, I get the whole reward. Instead, the model says, no, on average, I get like a reward of 3. So now I get a reward of 5, and what I do, the advantage in its simplest case could be saying, okay, just take the difference between what you got now and the average that you get, what is the expected. Therefore, you're really just looking for am I getting a tiny increase from the average or a decrease from the average? Do you see that? So essentially, it just provides that. It doesn't let the reward fully influence the training. It lets more like the difference of it. Okay? So that's the simplest case, but this could also be, many other things, okay? And this is one of the parameters that DPO, GRPO, TRPO all play with, okay? And if you make a change that makes it better, right, that you get to create your own PPO, okay? So even though the RT appears in the objective, we are not trying to maximize this ratio essentially because it's a little bit of a control. What we do want to maximize usually in reinforcement learning is the rewards. That's intuitive, right? We want to maximize the number of rewards that we get essentially. Let's think of the ratio. So what the ratio does, if the model is already increasing probability of a good action, then it's going to be greater than 1. So PPO allows a stronger update. So it's like I was getting a reward minus the average, then I have just the increment from the average, and then now I say, okay, the model is 1.1, so I bump that value a little bit more. Do you see that? So you are, and if you're maximizing that helps. It's like you're saying, do that. If the model pushes too far, KL regularization will push back, so that's the KL component, right? That's where was it? Here, right? The KL component also keeps you kind of stable. And then if the model reduces probability, right, that means that ratio is negative. So that's essentially negative because this had a lower probability than before. Do you guys see that? That's essentially what's happening. Okay, so either the probs for a given output, are higher than before or they're lower than before, and that kind of serves as a control for the reward. Okay, so if the model reduces probability, RT is negative. So probability of a good action or a token. So the update that's going to happen is weakened somehow. Yeah, go ahead.
Why are we still updating? If it's worse, why don't we just...
It's not worse exactly. It's just The reward is what tells you if it's worst or not. The ratio just controls if you increase your probability of predicting that term. So we'll see this in a second. So let me just finish through this, and then I have a little graph over here, so we'll get to that. All right, so that's, so insight, so the reward provides the direction of learning, right, the reward, and the ratio controls the size of the update. That's one analogy that you can use. So the ratio is in fact a break, not an objective. Do you guys see that? So that's kind of what it is. You don't want, for instance, that probability to increase too much because it's going to be clipped. Do you see what I'm saying? So if the probability of predicting that word given the input is very high now, then this would be 1.3. And if it's 1.3, that's too much. So then it gets clipped to 1.2, which is the clipping effect that keeps it between 1.2 and 0.8, I think. So now the other thing is, so this A actually here is called the advantage function, and you can look at it, it can get quite complicated. But one simple way of looking at it is the advantage function, you can think of it as the reward versus the expected reward. And I think the easiest example to think about is when you just think, what is the average reward in this situation? So for instance, as the model is training, keep a list of all the rewards. Do you see that? And then you can look at the last 10 rewards in that list and take the average. And you can use that as your baseline. Now you get a new reward, and you just take the difference of the two. And that kind of tells you, okay, we're getting rewards that are a little bit higher than the average. Do you see that? So you could have used full reward. But essentially what this whole thing does is that you are trying to optimize a reward, but with a lot of breaks. There's a lot of breaks all over the place. There's a break with the advantage because it's tying it to an expected reward. There's a break on the reward, on that parameter, even with this ratio and the clipping. And there's a third break, at least, with the KL divergence. And all of it so that all that work that you did with the pre-training and fine-tuning doesn't get thrown away. Do you see that? So that's one good way of trying to understand these things. Does this make sense, guys? Okay. So let's take a look at the reward. So here. So the advantage is defined as A equal RT minus V. This is called the value function. This could be another neural network, by the way. That's one approach. So you could have the GPT have another head. That's also very possible, and it could give you yet another probability. But to not have so much complexity, let's just think let's call it a baseline reward, so just the average. And we can all understand the average historically of something, right? That can be very valuable, right? Why, if my model always gets a reward of 5 in this type of problem, why am I getting now 17? You know what I mean? So having that average helps you out, okay? So where RT is the actual reward from the reward model. In our case, this is the BERT, correct? And then VT is the predicted expected reward, some kind of a baseline. So if in the interpretation, again, if RT is greater than VT, it's better than expected, right? The reward was better than what you usually get. If it's less than that, it's worse than expected. So some kind of a suppression or reinforcement. Do you guys see that? All right. This ensures PPO only reinforces actions that outperform the model's existing behavior. That's another way of putting it, right? So if you get a reward, 3, and the average is 3, what is that then? What is the advantage? 3 minus 3 is 0. Nothing, right? Do you guys see that? So that's another way of understanding this. So this ensures PPO only reinforces actions that outperform the model's existing behavior. Expected reward as a baseline, so the value head predicts VT. So this is sometimes the approach, which is essentially to have either another neural network or the GPT has a head to provide some kind of another reward based on what it's been trained on in the past. But any baseline works conceptually, okay? So for the sake of understanding, let's just consider a simple running average baseline. So this is, to me, more intuitive. So let, for instance, VT is the average of all past rewards, or the average of the last 10 rewards, or something like that. Then you just take, for the advantage, as I said, RT minus the average of the rewards. All right, so, and like I said, it just controls that difference. This still works, produces the correct learning signal. Reward is only meaningful relative to what the model expects. Okay, and like I said, I think if the average is 0 and the reward is if the average is 3 and the reward is 3, the difference is 0, so it zeroes out. The KL penalty, I think, is the easiest part of this whole thing, right? Hopefully. So to maintain alignment with the pre-trained base model, we use the KL divergence. Notice this is the policy of the new, which is like how I had it in the code, right? And the original, not old and, so it's definitely not old and new. It's old would be just the last iteration, for instance, right? Original needs to be at the very beginning. So if you have 1,000 iterations of this process, it's at before iteration 0, okay? And that's so it doesn't deviate from what you already had fine-tuned. Okay. So to maintain alignment with the pre-trained base model, this prevents reward hacking, distribution collapse, unsafe deviations, just complete deviation of this. Is this clear, guys? Does this make sense? All right, okay, good. Final insight summary. So reward is the true optimization target, as it is usually the case in all of reinforcement learning. So this is the thing we plot, as you will see in the Q-learning. This is the thing we're trying to optimize. But these systems have a lot of breaks. And that's a good analogy. So the ratio ensures controlled, stable movement toward high reward behaviors. Advantage ensures we only reinforce behaviors that exceed expectations, the expected versus the actual. Baseline, expected reward, prevents noisy updates, things like that. We can think of this as the averages. And then KL ensures the model remains aligned with its original distribution. GPT new compared to GPT original. So in PPO RLHF maximizes reward. Notice in the paper it just says optimizes. Right, so it doesn't even specify. I'm sure it's buried in there, but so far I've not been able to find that. But it's a reward. So maximizes reward using RT times AT, while the ratio, baseline, and KL ensures safe, stable policy update. So it's a type of very controlled optimization. Okay? Do you guys see that? All right. Now, I think this is your question. Hopefully this is... So as I said over here, we have the ratio, right? So the ratio, the KL is very standard. The reward is minus some other reward that's expected. But we're going to focus now on this ratio term to see how this might work. And keep in mind that this applies to just any neural network, anything that is a policy, such as playing a game. But in our example, we're going to now use it in our context, which is the policy is a GPT, right? So that's like you guys did in your homework. So we're looking at the GPT now and the GPT just like a step before in the iterative process. So we have to remember how these things work. And we say, as we have done over here, that we look at the log probabilities of old and new, correct? All right, so let's take a look. So here I have an example, and I have a diagram, essentially, right? So let's start with the diagram. Hopefully this gives context, and then we can dive into the text. So GPT scoring of a sequence, right? So what do we know about GPTs? Autoregressive, right? We give them a sentence. What do? They produce a sentence, correct? So do you guys remember in all the assignments that you've done, whenever you ask a question to a GPT, any question, it provides the answer, right? But before that answer, what does it always return? The question, right? So you give it a question, and then you get the question back, and then your answer, correct? You've always seen this in your GPTs. It's always, do you know what I mean? And that's because of the nature of how GPTs work, right? So GPTs, essentially, now these arrows represent the GPT, right? So this is the input, this would be the output over here. So remember that when we train a GPT, how do we train it? We have the GPT, and I have a sentence, and we use teacher forcing during training, which means that we use the same sentence as input and output, but they're shifted by one. We've established that. Why do we do that? Because if we just let the model generate its own tokens, over time it would start generating noise, errors, so it's going to train badly. So during training, we use teacher forcing. That means the sentence is always correct, right? Same input as output, but just shifted by one. So essentially, remember, the only thing that gets predicted, actually, is the last word. Everything else is kind of a repetition, but shifted. Do you guys see that? Yeah? All right, good. So we have sequences of 40 and so on. So in this example, for instance, I have the fast car is faster than light. Okay? That will go into a GPT. And in theory, right, so the fast car is faster than light, then you get the same sentence shifted, right? So by one. So here is fast car is faster than light, and whatever the prediction would have been. Do you guys see that? So then, essentially, this is a way that you can get the log probabilities of old and new, right? Because usually you would just look at the last word predicted of old and new, but if we give it the whole sentence, it's got to generate this again, right? That's why they're fixed. So sequence, tensor, that is batch, comma, 40, comma, 512, batch, comma, 40, comma, 512. The fast car is faster than light. The fast car is faster than light, but shifted, we grab faster than light, speed, right? Speed would be the prediction. We grab that one. What do? We concatenate speed to the input. Goes in again, shifted by one. Faster than light, speed, in. Grab in. Faster than light, speed, in. Space, and so on. Do you guys see that? So it's only the last word that's but we're always getting that tensor. So that's how we use it in the generative mode, right? But there's also the training mode. And we don't change the architecture between training and generative, right? So, okay, so now so then if we establish that I can so now we have same architecture, right? We have GPT old and GPT new for that policy ratio. Everyone with me? It's the same one. We just label one old because it's one iteration behind, and then the current one. So what we can do is then the question and answer can be given as an input, for instance. So I have, how is the stock market doing tomorrow? It's going to do really great. You should invest in this, right? So that's now we get that question and answer concatenated, give it to the GPT, and we can give it to the both old and new. Do you guys see that? And what's going to happen is, do you all see that? So I give the exact same sentence, right? So let's say the fast car is faster than light. It goes in. They both just predict kind of the same thing shifted by one, and each one is going to predict maybe a different word here. But we don't care for those words. Those we can ignore. And what we look at then is fast car is faster than light. That's going to come out from old and new in the exact same position. Do you guys see that? And that's the key. So now you can compare both of those, but what's going to be different? The props. Because remember that we don't get the word first, right? We get the word last. Before the word, we have to get what? That head, right, that takes the embedding and maps it to 50,000 with a probability distribution that is softmax. So now you are looking at a way of calculating probs for a sentence. So essentially, the GPT can become a GPT scoring machine of sequences. Do you guys understand? Any questions? That's it. I mean, I don't know what else to say. Go ahead.
But the score that we are getting from a sentence is just the probability of the next word, right? Like
It's the probability. Yeah, it's the probability of the next word, but it should. So again, when we give, every time you give a sentence to a GPT, it repeats that same sentence to you, and then it starts generating. Correct? This is, yeah, go ahead, please.
So we want the same tokens back so we can compare the probabilities.
The probabilities, yeah.
So if we get a different token, so if by some chance, like the logics come out and something else is more likely, then does that blow up the ratio and take us into that clipping zone?
I mean, in my experience, whenever I give something to a GPT, I get that back.
Okay.
So essentially, I see what you're saying, but I've never seen that happen, actually.
I know it's probably a real small chance
Yeah.
that happens, but that would...
You would still use that, because you have to use something fixed, right? So you would still use that.
Okay.
And that's what I would say. So in this example, you know, let's say the fast car is the question, faster than light is the answer, we concatenate it, we give it to it, the transformer. Yes, it's given that sentence, is going to, it needs to, I already know the fast car is faster than light. I don't need it to, what it needs to give me is what follows there, right? But the way that GPTs work is that you give it that whole thing as a token, right? You give that as a token. Remember how it works. I'm going to take that sentence, split it into subwords, right? Each one of those is a number, and that sequence goes in, and then each one of those becomes a vector of 512 or 256 or whatever it is, and boom, it goes through the network, and it's going to predict the next one, right? And so whether that happens or not, this is how it's expected to happen and how we always see it happen, right? Because we always get the question back. Yeah, go ahead.
so when we say we get the probabilities of a given sentence,
Mhm.
like the probability of that sentence be phrased in that order.
Literally the numbers that we get here. We just take, remember how, so let's go to the whiteboard. Let's remember just the code itself, right? We're not changing anything. We're just using what exists there. So we have here, I'll use, what was it, the fast car light speed, right? So I have a GPT. The fast car is, right? So these go in, right? But they become IDs first, right? And so they become IDs, then they become like embeddings of 512 each. So 512, 512, 512, 512. When we train a GPT, essentially it's predicting the net, you know, we just give the sentences shifted, right? So over here, let me do it over here. So it would be fast car is light, something like that, right? And that light was not in the original one, right? That's usually the only thing that we take as a prediction. When we're in generative mode, then all we do is we concatenate this to that, and then that becomes the input. Then we get the next word and so on. We have to kind of, if you remember, right, that's exactly the code that we've looked at. And so we're just keeping, and that's how the generative process works. So what this is saying is we have old, and then you have new, which is just one iteration in the future. Right? New. And what do we give new also? We give it. So we're just testing how these probabilities have changed, essentially, from one iteration to the other. Right? So the fast car is. You see that? And then this produces, and I'm skipping something there, fast car is, let's say here it predicts dark for whatever reason. Okay, sure. Do you see that? But we're saying, okay, this is essentially the fast car is. We don't even know what, we never look, right, at that prediction, essentially, right? But this is what is expected. Do you see that? And then remember, over here, we have the final 512, the final embedding. Oops, sorry. 512. And then what did we usually have in that after this? We would have a final feed-forward layer, right, that embedded to the vocabulary. Do you guys see that? So then this would, what is it? It's a neural net from 512 to 50,000, if you guys remember. But softmax also, so it's kind of like a probability distribution. So then here, this becomes, I'm going to make it a little bit bigger, 50K, 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 50K. These are the probs, like from which you calculate the log probs and all of that. But these are like the original probs. Do you see that? And now, over here is the same thing. Okay, so 512, the embedding. 512, the embedding. 512, the embedding. 512, the embedding. And then, we had in the final layer, if you remember, just something that maps from the embedding size back to the vocabulary size. Because when we train, we have those vocabulary IDs. So this is 50K, 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 50K. So this part here, this is it. Do you see that? This is how we can calculate a ratio. So we are giving, we can use essentially a trick to get probabilities of this sentence from the GPT itself. Because we give it the same sentence, the fast car is, it produces something to go to, actually, if I think of your question now, so maybe it would say, instead of fast over here, it would say speedy. The speedy car is. But do you see that it's still semantically what it knows? Fast versus speedy. Because at the end of the day, to us, fast and speedy is different because we're human. We understand things in that context. But the transformer never looks at the words fast and speedy. It's only looking at an embedding of 512 and an embedding of 512. Do you see that? So it's more, it kind of works still, I think. So if that happens. But essentially, this is, what you can expect in this, in this context. So what I'm trying to say is it's okay to just do this. Because you do need something, apples to apples, right? You do need some kind of apples to apples. The behavior is usually that you feed this and you get that output back, or so in teacher forcing. So if you think in the context of a pre-trained model, we give it the whole internet, right? 3 months, 1,000 GPUs, and we for sure I can tell you, in teacher forcing, I'm giving the sentence for input, the sentence for output, the same one just shifted by one. So the expected behavior is always the fast car is light. Guaranteed. It's a massive training, right? So then you can have some confidence that this is going to work when you put it in inference mode, right? And you can say, okay, I give it the fast car is, in theory with some deviations, such as the speedy car is still acceptable, right? Because actually, what are we measuring? We are measuring when that probability changes that it became speedy, and not the black hole car is. You know what I mean? That's a massive change. At the end of the day, speedy and fast are still okay. But maybe that break is to keep that from. What would be like for instance, if, I'm trying to think, like if I'm in the Lord of the Rings world, is there a word for fast and speedy that is just very elvish something, right? They're faster than normal. So do you see where I'm saying? So that went too far. Don't speak in elvish to me about fast and speedy. Keep it to normal, fast and speedy. Do you see what I'm saying? So I know this is sometimes hard to interpret because it literally becomes the language that we use, but what I'm trying to say is we have so much confidence in how we train with teacher forcing, which guaranteed same sentence input and output shifted, and we know that it looks like this, then we can say, okay, this is in inference mode somewhat apples to apples. We give the fast car is to the old and the new, and then we just focus, let's say, because the last word is a new predicted, right? So let's just say then that right there. For that, and that right there for that, that's mostly apples to apples. You see, and now I can calculate those probabilities however you want. You can concatenate all the vectors, whatever you want to do, take out one value, right? But the idea is now you're, because remember, this is a tensor of batch to sequence, let's say 40, to it was 512, which will become 50,000, which will become the ID that you selected. But when you go to the ID that you selected, you've gone too far. So you need to actually stay in some way that has something close to probabilities, which in our case, the only place where we have that, two places that we would have that are the embeddings, possibly, right? Or the actual softmax vector of 50,000, which represents more the probability of the ID that I'm going to select. Do you guys see that? Yeah, go ahead, please.
Well, the model always outputs the same phrase as we input, right? So when we
the model always, say that again?
The first words of the output are always the things that we have in the input, right?
Right, that's in teacher forcing, that's how we do it, so we can reasonably expect that that would happen in inference.
So getting the probability.
Especially, sorry to interrupt. They are originally the same one, right? The same model. They're just being, and this is in fact, also the other thing is we're just looking at the iteration now and one iteration in the future. Like, that change is not massive. So even for the example of speedy, well, that assumes that 100 iterations have happened into the future. You see, you're literally comparing me to me a second from now. versus me to, next year. Oh yeah, I'm going to be very different. I'll forget everything I've done. So, do you see what I'm saying? So that's also one way for me to answer your question. It's probably not going to be speedy because it's only me like a second later, one iteration in the future. That's kind of a break that I have. Any comments, questions? Yeah, go ahead,
I
please.
think this helping. I don't think it matters if you get speedy because the 50K, we're looking at the probabilities for the whole vocabulary, right?
Yes.
So it doesn't matter which one's most likely. You can pick a different word, but if you're looking at all the differences across all the words.
We're looking at the
it really
differences,
matters.
yeah.
I think that's what the KL measure does.
But this is not KL. This is for the ratio.
Okay.
But the KL would also do that.
It's the same type of thing.
Same type of thing, good, but we have a third one. And the third one is exactly, this was new, correct? This was new, this was old, and this is original. That's the only difference. So that we start at original, and then we start training. And it becomes new in the first iteration. In the second iteration, we get a new, and old new becomes old. We just save it. Do you see how that works? So yeah, you're right. Actually, your logic is totally correct because they are in fact the same, and it's just as we train, things are changing in the weights, right? A little bit. One controls me and me next year, right? That's KL. And one controls me and me a second from now. So I'm more likely in me a second from now to say the fast both times. But I may say the speedy next year, where I would have said fast in original. Go ahead, please.
The thing is,
Yeah.
if those are the probabilities of the words in the input, it is never going to say speedy in that specific position of the sentence, right? Because it's part of the input, so it's always going to have fast.
It's always likely to have fast. Yeah, I mean, it is not is not always, as he said, is not exactly guaranteed that he's going to say fast, but in training, when we train like this. The fast car is light. So it's a reasonable assumption that from step 1 to step 2, it's kind of the same. But as we get further apart from it, yes, I grant speedy is a possibility. Still in the context, right? But you see that? So, I mean, it is possible, as he said, that from iteration 1 to iteration 2, this should have been fast. It could have been speedy here. It's possible. It's not impossible. Because the model can produce whatever it wants, right? So it's not like it always just goes 100%. It's always going to be that sentence. It is still predicting. But from iteration 1 to iteration 2, very likely. Yeah, go ahead. Uh-huh.
What I was thinking is, even in our lab,
Yes.
you input random words, it
You-
still outputs those same random
Those same random words, yeah.
Yeah, so I was wondering how can it change the words in it? Like if you put cat, nuclear, tan, it still give you the same word.
Cat, nuclear, tank, and then the rest.
Yeah, even
Yeah.
though they are not probable, like it's impossible that it predicts tank after cat and nuclear.
Mhm.
That was what I was thinking.
Yeah. Right, but I think get away from that idea. I think maybe that was a bad. I'm starting to regret saying that. You don't think of it that way, right? Just because it's still predicting, but what's more true is that inference is like one little this. Like let's take a beach. A whole beach is training. One prediction is like a grain of sand. So what we're saying is we trained it for a long time, right? And during training, during teacher forcing, the fast car is light. Guaranteed. No question about it, right? Now, in inference mode, yes, it's possible that we give it a sentence. It should, right, predict something else. But now the thing, okay, then you would say then this won't work. But from iteration 1 to iteration 2, the model has changed very little. So this teacher forcing is more likely from iteration 1 to iteration 2, but speedy from original to new, yeah, more likely. Do you see that? So it's almost like it itself is a probabilistic assumption. Nothing is 100%, but in terms of likelihood, this is the thing. And remember, again, what are we doing? We are calculating the probs, right? So this is the probs of what? Old. And this is the probs of new. And what were we doing with these? We were calculating a ratio, right? So this is, let me do it over here, ratio of probs of old to probs, wait, so do new, I think new goes as the numerator, so give me a sec. Probs of new, probs of old. Do you see that? So what we really need is, we need like, the key question with this ratio is like, it has to be apples to apples somehow. Okay, let's see if it passes the apples to apples test. GPT old and new, one iteration apart. Agreed? Yes. Input that goes in to both, same. Agreed, apples to apples, passes. What comes out here is expected because of teacher forcing and how we train things, is the same sentence shifted by one for both cases. So this one is maybe not as guaranteed, but from one iteration to the next, yeah. So then, essentially then, it's not so much a probability. Another way of thinking about this, which might help, is that it's not essentially a probability that it went from fast to speedy, right? That would be like a whole transition, but it is just in fast. Is it more likely or less likely? Like in the fast before, it was 0.80. In the fast new, it is 0.20. Guess what? It went down, and maybe speedy was 0.30, so now speedy gets chosen. Do you see that? So you can think of it that way. Yes, sir?
So actually, I try to understand here, the fast is actually transition into speed.
It's right. We essentially pick a word, right?
Yeah.
We're going to pick in this vector, 50,000, we have all the words, including speedy and fast.
Yeah.
Right? So what I'm saying is we are looking at these probabilities. So if old had a probability of 0.80 for fast, that was going to be selected. It was a high probability.
Because inside the knowledge search vector fixed speed because the fast and the speed looks similar into this context. Am I right?
That's right. Remember that what are we changing? We don't change the probabilities, right? What do we change when we fine-tune a transformer? The weights.
Yeah.
The weights. So what's happening is all these weights in here are being updated. That's what gets updated. But in the end, these weights produce a final embedding. If you guys remember, batch, 40, 512.
Yeah.
But there's nothing we can do with that. We still need to have one more head that converts that embedding of 512 to the embedding of 50,000, the 50,000 tokens. You might remember that's from 520, and then that's a softmax so that that sums to 1, and we pick the word with the highest probability. Do you see that? So all this is saying is old fast was 0.80. The updates of from one iteration to the other, new might become 0.20. Speedy was 0.30. Speedy wins now. And out comes speedy. But this is more trying to control these probabilities, okay? For all these things. That's the assumption. It would be too hard, in fact, and it's not trying to change the code or trying to change the architecture of the model. It would be hard to say, I'm going to focus on that word fast or speedy or whatever, because how do you know it's speedy? Maybe it's a third word that indicates going quickly, quickie, or something like that, right? So that's the idea. So essentially then, you just look at the whole tensor itself, right? But you have this assumption that essentially they are predicting the same thing. They're going to be the same dimension, minus the last word that you're predicting, which you can skip if you'd like. Do you guys see that? And so that's essentially the idea. So we get a ratio then of the change between probabilities old and new. Yeah. So, and that's a way of controlling the update. So actually, maybe we didn't want it to become speedy for some reason. We wanted it to stay within the world of fast, right? So 0.8 to 0.20, okay, let's actually take this a step further. So we got ratio, right? Just one word. This is new. This is old. So this was what? 0.80. This would be like 0.20. And that serves as the ratio of this ratio of the change between the probabilities is then, let's do it over here, 0.20, 0.8 to the reward itself, which is from the advantage function, right? So it's a kind of a control of how much did this change over here. Do you guys see that? Any questions? This is, this concept is maybe difficult, but this is the essential idea. So we can go back now. Let's share the screen. So now going back to this graph, right? So this was the idea of the graph. Remember, so we have two models, old and new. The models get in, let's say, the question and the answer. It provides, obviously, the words, but before the words, we can reasonably expect, well, it provides the probabilities then, and those become the values that we can compare in the ratio itself. Okay? So that's the diagram. So let's take a look at this a little bit. I have a write-up here. So GPT scoring a sequence. And this is the intuition of the log prob. So when GPT is given a complete text sequence as input, it always returns next token logits for every position in that sequence. Okay? Well, as this indicates. We can give the same text to both the old GPT policy and the new GPT policy that make up the ratio. And definitely for this ratio to make sense, it has to be apples to apples. Like follows, and they can help provide the probabilities. Example in input sequence, so the fast car is faster than light. GPT old and new returns log probabilities or logits, whichever one you want to use, for each token in the sequence. Fast car is faster than light, and the next token after light, which can be ignored. So this process is simply log probability evaluation of a provided sequence. Question and answer can be given to the old and new GPT for scoring, and then essentially we can calculate the ratio that controls how much things are changing. It might be hard because there's a lot of, but let's just imagine we just have one thing that we were predicting, right? So then we would have one probability that we predict for that thing from the new and the old, just one iteration in the past. This is a key assumption, right? This works because it's just one iteration in the past. So it's reasonably expected to be somewhat similar still. And that's it. All right, so that's it as far as that. So I'll just again summarize. by, through the equation. So the goal of PPO essentially here is this loss function. It's got 2 or 3 breaks and 1 objective. To optimize the advantage function. The advantage function is really the reward minus some baseline, which I wrote over here. Okay, so this ensures PPO only reinforces actions or generated text that outperforms the model's existing behavior. So it's just that incremental. Like in calculus, right? It's always about like the differential of something. Okay? So that's the advantage function is in terms of the reward multiplied by this ratio, which I didn't include the clipping, but remember that's like saying, okay, if the value is between 1.2 and 0.8, it's fine. Use that value, otherwise clip it to that. So don't let those probabilities get too extensive. Maybe the example of going from 0.90 fast to 0.1 fast, where it actually flips it to another word like speedy. And then minus the KL divergence, which just is a technique from information theory that calculates like the difference in distributions, again using the same principle but between old and new. All right, guys, so are there any questions on this? Any questions? Make sense? All right, so that's that. Reinforcement learning can be a little bit tough. The other methods like DPO and other ones are similar to this idea, but they have, the advantage function might be a different thing or doesn't exist altogether. They try something else, and so they deviate from this essentially. All right, so that was the theory on on reinforcement learning through human feedbacks with PPO. Okay, so it is 7:44. All right, so let's stop here. This is a good stopping point. Let's come back at 7:54, and we can do a few presentations of whomever is ready to present today. And then after that, I still have the Q-learning with neural networks, so we can take a look at that. That's going to be code, so you can take a look. All right, so let's stop here for this one.